All right. Today we will do the vertically driven inverted pendulum. This is an example of slow effects of fast excitation, and we will use the method of multiple scales. Let us write equations. So now here is some surface, some line rather, and here is the base of the pendulum, to which we impart a displacement u of t. This is external. We will think of the pendulum simply as a point mass m, a rigid rod length L. Let this angle be theta and let there be gravity g. All right, the acceleration of the mass is equal to, now there are two terms there you may remember from rigid body dynamics. So let us say this is ER and let us say E theta. These are our unit vectors. The acceleration is equal to minus L theta dot square ER plus L theta double dot E theta. This is actually the acceleration of the point mass relative to this pivot point P, but then there is the acceleration of P itself, for which it is better for us to use unit vectors I and j and write plus u double dot j. So that's the acceleration of the point mass m. Let's draw a free body diagram of the point mass m, because this is a point mass and that is a massless rod. So if I draw the whole rod and I say that there is a point force here, then there is no place for me to put viscous dissipation. So let me say that there is a, let's see, we can put some kind of fake dissipation later, but it may be useful to do it here. So let us say that there is a moment here, a frictional moment. This is a frictional moment. C theta dot minus, because theta is going clockwise here, so we need to do it like that. Okay. Now, so over here there is, at this point in the free body diagram, now that this is a free body diagram, this here, there is some arbitrary reaction force R and a moment like this, which is C theta dot. Okay, all right. However, it should be clear to you that the net moment about this point here, the net moment about this point should be 0. Why? Because moment is j theta double dot in planar dynamics. And about the center of mass, j is 0. Okay, so since the moment is c theta dot, this is some force here, it is actually easier for us to do angular momentum balance about this point. Okay, So we will do it like that. So if we revise our rigid body dynamics, then what we have is, if this is some rigid body with a center of mass at G, this is some arbitrary point C, then what we have for rigid body dynamics in 3D is we have sum of vector moments about C is equal to the position vector from C to G crossed with the mass of the body times the acceleration of G, G being the center of mass, plus ICM alpha angular acceleration vector, plus omega of the body crossed with ICM omega. So this is sum of moments about C is due to whatever there may be. So there may be a force here, there may be some applied vector moment m0, whatever those are, we calculate the net moment about C, and this is the equation we get. Some of you may be accustomed to the idea of taking the angular momentum balance about the point that instantaneously coincides with G, in which case this term would be 0, and in planar dynamics this term is 0. Okay, but now we will take care of these two terms. Okay, to do that we have to notice that omega is equal to minus theta dot k, because theta dot, we have taken it to be clockwise over here, the way we have gone about it, and k is out of the board. Okay, we will therefore write alpha is equal to minus theta double dot k. We will write, let's see, ICM is equal to 0, because it's just a point mass. So in fact, in our case, this is also 0 and this is also 0, you see. And so our equation becomes like this. Let us take from this free body diagram, the moment from this about C is also 0. The moment about point P, we are taking angular momentum balance about P, so it is C theta dot k. So we come here, this one is C theta dot k is equal to, this one is L ER and what this is, you know what that is. Minus L theta dot square ER plus U double dot J plus L theta double dot E theta. Okay, this is our equation of motion. It looks like a vector equation, but there is actually only a k component. Okay, all right, let's calculate these terms here. ER, so this one goes off in the cross product. ER cross J we have to figure out. So ER cross J, if we look here, ER cross J is sine theta in the k direction. So we have C theta dot k is equal to L U double dot sine theta k. I'm very sorry, I've made one mistake here. Terribly sorry, please correct it. There is also mg. the weight of the body. And because of this reason, when we come here, this is going to be minus mgl sine theta k. Please check that. So over here we will have minus mgl sine theta k plus c theta dot k is equal to, and now I am evaluating the cross product between this one and this one, that is lu double dot sine theta er cross j, which we have determined is k, and then we have to do the other one. So let's go back and do the other one, er cross e theta. And that's easy. Er cross e theta is minus k. So we go there and we write minus L square theta double dot k. Of course, remember that there is this m sitting outside, so we have to come back here and multiply this right hand side with m. That's our equation of motion. Let me write it out a little more clearly. So what we will have is, let's see now. I'm going to move this term over to the left hand side. The k and the k and the k cancel, no problem, it's a scalar equation. So I'll have m L square theta double dot minus m g plus u double dot L sine theta. What have I taken care of? I've taken care of this term. I have this m u double dot L sine theta. I've taken care of this term. mgl sine theta, I've taken care of this term, and then I have plus c theta dot is equal to 0. Very good. What we will do now, I think, is we will divide by ml squared, and so we will have theta double dot, and then over here I will have minus, and for g by L square I will put some number, like I'll put a, and for 1 by L square into u double dot, what I will put is plus some little b u double dot. Right? So this, the L is gone, the ML was in the denominator, G by ML is basically A, and so on. So this times sine theta, and then over here plus some C bar theta dot equals 0. This is what I'm going to look at. Further, I'm going to say that u is equal to u0 sine omega t. So this is the oscillation that I am putting in the base. Okay, so that's fine. I'll say that. That means that u0, okay, so it doesn't matter, we'll come here, we'll have theta double dot. I hope you don't mind if I change this a to just 1, okay, because just number, some choice of units of time. So I will have plus c bar theta dot minus a plus, and this b and the u0 and the omega square are all going to combine in some way, but I will just write it as b u0 omega square. I should have made this minus because there's a derivative. It doesn't actually matter, but because we are being a bit careful, we will write minus. It won't matter. Minus or plus, and then over here sine omega t times the sine of theta equals 0. So this again is your vertically driven damped inverted pendulum. Okay, let me minimize this and we will move to MATLAB now. Move to MATLAB, and I am going to disconnect my board here. Give me a second. Let us let's move a bit like this. Let's move this a little bit out. Let us start a new script and get this one down here. Function q dot equals vertpend for vertically driven pendulum tq. Okay, now what I'm going to do here is I'm going to use epsilon equals 0.06 or something, some number, and then I'll say capital omega is equal to, let us say, 2 by epsilon. So you can see that it is a rapid excitation, and I will say u0 is equal to, let us say, 1.7 times epsilon. Okay, and I will say let's see, maybe I'll make this 0.04 or something. Okay, and then I will say b equals 1, who cares. Okay, so some number. Now then in my equations I'll have q dot equals, and I'll have q2, that part is easy. I need a c bar. C bar equals 0.3. Let me say that. Okay, now let's look at our equations here. So minus c bar theta double dot, right? So minus c bar times q2 and then plus, and then I'll put, for a I will put 1. So I'll have plus and then a minus b, right? So we'll come here, plus 1 minus b into u0 times omega square times the sine of omega times t times the sine of q1. Okay, so this is our vertically driven pendulum. We will have to give it an initial condition that is different from 0, but maybe not very big. So that means when I give it an initial condition that is not very big, I want you to realize I am giving it an initial condition where it is close to vertical, right? All right. So we will come here, let us say OP equals ODE set. All right, and I say TQ is equal to ODE 45, vertical pendulum 0, 30. Some small initial condition. And when we look at t and theta, you will see that it has stabilized near 0. So the pendulum has actually stabilized near vertical. How did this happen? Okay, so this is what we want to understand. If you look here, there are fast oscillations on it, that is from the driving frequency. Okay, and you will see here that the initial conditions are not that big. We can do this again. Sorry, obviously you'll get the same answer, but with some other initial condition. It's not special, you know, it sort of decays to 0. Alright, let us take this u0 and make it 0.7 and then try. And this time you see it diverged from 0 and it is settling down at pi. That means the pendulum did not stabilize in the vertical position. Okay, so this is the system we are going to try to understand, and we will try to understand using the method of multiple scales. Okay, so let's go to Maple. Well, before we go to Maple, what I will do here is I'll warn you that I am going to set T0 is equal to omega t like this, and T1 is equal to T, and T2 is equal to this T by omega. But of course I will just say omega is equal to 1 by epsilon, and then what will happen is here I'll have that singular time. So my fastest time is the time of the individual oscillation in the forcing cycle. My time of primary interest is the time order 1, and then this is the slow time over which we will have to do the calculation to get something meaningful. Okay, so let us come here and just get the thing started in Maple, and we start like that, and what we do is we say dE is equal to theta double dot times omega square plus, what happened here, plus C bar times theta dot minus 1 minus u0 times omega square times the sine of omega t times the sine of theta. This is our differential equation. Okay. However, we will now come in here and do a few things. So we will say, we'll write it again. I will remind you that u0 was order epsilon and omega is 1 by epsilon. So I will come here and I will write it again. For my purposes, I'll call this dE1, and I will put here by epsilon squared. Okay, and because that's omega. Why did I put here theta double dot times omega squared? I should not have put it. I'm very sorry. It will come later. I don't know what I was thinking. I hope that's better. This one is definitely there from the derivative we took. Okay. Now this one becomes u0 by epsilon. Why? It becomes u0 by epsilon because u0 is actually some u0 times epsilon, and then this omega is 1 by epsilon. Over here this becomes t0, but we will remember that that is our fast time. This one is not needed. Okay, so that's our differential equation now. And then what we will do is we will say n equals 2, and we will say our t's are the sequence t, k, k equals 0 to n, and we will say THS is equal to add, and we will say, since I have that theta, I will just call it x now. I hope that's okay. So xk of TS times epsilon to the power k equals 0 to n. Okay, so that's theta. Theta is now x, and this is the expansion. We always do this. Then we come here and we say theta dot is equal to add diff theta tk times epsilon to the power k minus 1. This is the main difference from what we have done before. I hope you notice what we are doing. This is because T0 actually is little t by epsilon. Okay, so that's what makes it fast. Okay, so that's fast now. And then THDDS is equal to, of course, that's just a repetition of this. So this just becomes THDS, and I suppress the display. So I've got that now. And then I have to go to DE1, which is here. Okay, so I go there now. I say DEA is equal to substitute THDDOT, right? Theta double dot, no, theta double dot, I have to write it out, is equal to THDDS. Theta dot is equal to THDS. Theta is equal to THS in DE1. And this will be a bit long, but we can suppress the display. Okay, and then you see it is better to multiply by epsilon square to make things a bit easier. So let me just times epsilon square, and then I can say expand or whatever and suppress the display. Then I say DEA is equal to Taylor DEA epsilon n plus 1. I don't know where we'll land, but we'll see. Let us look at it. Okay, so here we are. This is all order epsilon. This part is order 1. This part is order epsilon square, and I think we are in good shape. And so what we will do here is I will say convert that to polynomial. Okay, now let us look at the coefficient of DEA epsilon 0. That is the leading order term, and you see this thing is just the second derivative is 0. So we should think of it as a plus b times t0, but because b times t0 will grow rapidly and make the expansion break down faster than necessary, we will take x0 just to be some function a of t1 and t2. Okay, so for this reason we will say temp1 is, and we will say this thing here, control C, is just equal to a of t1 t2. Alright, we'll say that. Now we will say THS is equal to substitute temp1 THS. We will say DEA is equal to expand substitute temp1 in DEA, and then after we expand we want to collect for epsilon. Okay, and this may become a bit long, but no, not that long. Okay, so here now we have the order 1 term and we have the order epsilon term and the order epsilon squared term. The order 1 term is dead. This is DEA. The order 1 term is taken care of. Very good. So now we go to the next order and we say temp is equal to the coefficient in DEA of epsilon to the power 1. Alright. Now you look here and you see this is the second derivative of x1. So x1, and it's a linear differential equation for x1. Okay, sine of a is nonlinear in a, but for x1 this thing is just a forcing term. In this forcing term, what happens is t1 and t2 are constants as far as t0 is concerned, because we have this PDE. Okay, so this is a linear differential equation. It will have a complementary solution that has a constant plus something in time. We are not solving an initial value problem, so we can just take that to be entirely 0. No problem. Here it is this part for which we have to make sure that it does not have a non-zero average. If it has a non-zero average, in that case, that non-zero average will contribute to a parabolically growing term from here. If it had a non-zero average, we wouldn't know what to do. Okay, but look, it doesn't have a non-zero average, and so I can integrate this. Okay, so I can solve this. So I can say desolve temp for this one. And Maple is clever enough, gives us an answer, but this f1 and f2 can be set to 0. f1 has to be set to 0 because otherwise the expansion will break down. f2 we can keep, but we don't need to keep. Okay, so what we do is we say temp2 is equal to substitute f1 equals 0 and f2 with, it has this funny underscore, okay. So now I've got this here. This is temp2. Very good. So I say theta substitute is equal to, theta s is equal to substitute temp2 in theta s. So now I've got the solution up to here, but of course, as you are familiar with by now, we are really interested in this. Okay, because this is order epsilon, it doesn't matter. This is the main action here. This part has rapid oscillations of small amplitude. We have seen that in the MATLAB solution. Okay, and we will have DEA is equal to expand substitute temp2 in DEA, and we will collect for epsilon. And if we have not made a mistake, there will be only order epsilon squared terms. And that's what we have. It seems like we are just crunching along, but actually no, there is something nice about to happen. Okay, very good. So now we say temp equals the coefficient in DEA of epsilon to the power 2. And here we are. This is x2 double dot and the rest of it is forcing. It will go to the right hand side, have a negative sign, but that'll be forcing. If this thing has a non-zero average, in that case this one will have a parabolically growing term, and that parabolically growing term will cause our expansion to break down. And so far we have not said what A is, but now we will say that A is whatever it is that makes sure that the non-zero average, the T0 average of this is 0. That's easy enough. We know tricks to do that. We will just temporarily set this equal to 0. So we'll come here and say temp1 is equal to substitute that thing equals 0 in temp, and we will expand that out, and we will do combined trig on that so that we can see a little more clearly. You see, This part does not have a non-zero average. This part has a non-zero, sorry, this part is a non-zero average. It is not oscillating. This part oscillates, it has a zero average. This part oscillates, it has a zero average. This part oscillates, it has a zero average. It may be simplest for us. Let us try here. Temp2 is equal to integrate temp1 t0 equals 0 to 2 times pi. I can divide by 2 times pi, but actually because I am going to set it equal to 0, it doesn't even matter. This thing has to be 0. This is the condition that thing must have zero average. And here is something nice. You will notice that the T2 derivative of A has not appeared. So this is, A is the averaged quantity, you see, it is the mean part, it is not the oscillating x1 part, it is the order 1 part. And since T1 is the same as T, you see, so this is just like getting the averaged equation here. So what we will do is we will say temp3 is equal to substitute, and then we will say we will say control C, we will say this one is equal to theta of T1. Temp2, and we will say expand. Okay, so this is our equation now, and this equation is going to work with us. You will see now that what happens for small theta. What happens for small theta? Let us do that one. You will see this is of course C bar theta dot. This is theta double dot. There is a minus sine theta, and there is a sine theta, and then cos theta u0 square by 2. So if you think of small theta, this is like an oscillator inertia term. This is like a damping term. This is like a negative stiffness. For small theta, this is minus theta, and for small theta, cos theta is 1. So it is u square by 2, and so the coefficient of theta is actually u square by 2 minus u0 square by 2 minus 1, and therefore u0 square equals 2 is the stability boundary. Okay, so u0 equals square root of 2 is the stability boundary. But let me come here to MATLAB and what am I doing? And add another equation. Okay, so what I will do here now is I will add another equation, and that equation, two equations. So what I will say here is q dot equals q dot and then q4, because now I am writing two second order equations for the A part. I hope it is clear. If you look at it slowly, maybe pause it, it should be clear to you. And then now we have to write the other one. So this one is going to be minus C times A dot, right? So there we are, minus C bar times Q4. Okay, very good. This U0 I have to write 0.7 or whatever it is, you know. So there is that's one problem. I will fix that. You will see what I'm doing. U0 in our case now is this 0.7. The omega I had written as 2 by epsilon. That was another problem. Let me say omega is 1 by epsilon first, because that is what I have done in the other case. Let me say U0 is equal to 0.7. Then let me come here and say by epsilon, and the b was 1, so let me just get rid of it, and over here I can get rid of that. So I hope you will agree that I am now doing essentially the same equation, no problem. And then over here c bar times q4, so we are here with the negative, and then with a 1 minus u0 square by 2 cos theta. Okay, this theta is our a, this theta is our q3, so plus 1 minus u0 square by 2 times cosine of q3, okay, and that times the sine of q3. I hope you will agree that this is our averaged equation. Let us come here. According to this equation, with u0 less than square root of 2, it should be unstable. We will do that here, but what we will do is we will take q0 equals our initial condition. So for theta we will put 0.2. For theta dot we will put 0 because that x1 term is there and it's a bit complicated. 0.2 and 0. We will try this. Some nearby initial condition should be allowed, so we will have to check on that a bit, but other than that it should be alright. And then over here we have q0. Let us look at the answer. It won't match because of the initial condition. We will plot 1 and 3. So it's not quite matching because of the initial condition. Instead of minus pi, it has gone to pi. This initial slope can be changed. We can change it for the red one. And what we can do is we can say minus 0.3 or some such. I'm just guessing. Oh, that was too far. And just 1 or 2 more we will get it. We can calculate it. I'm sort of avoiding that, but you can see that it is working. Okay, so you can see that the match is really very good. This is a waste of time now. Okay, so you can see that the match is really good. I am not plotting the same function twice. You see, one follows the average and the other follows the oscillating part also. Let me remind you that I am using a different order 1 derivative here. That is because the true solution has this one here, and so T0 introduces a very fast change, you see. So although there is epsilon 1 here, when I take the derivative of this with respect to even T0 as the first cut, it gets divided by epsilon, and so I get a large initial condition here. Okay, so because of that initial condition I have to take care of that. I can take care of it through this calculation itself and say what it should be, but I hope this is okay. So now we come here finally and let us do something more than square root of 2, like 0.7. And now once again I think this u0 was there, so I might as well multiply this a bit. I'm just wondering whether this is enough. I'm just wondering if that is enough. I'm doing this calculation a bit quickly in my head. Yes. So you see now there is this oscillatory part and two solutions are there and they are quite close. If I change the initial condition very slightly more, it will match better. I can say Q0 equals maybe 1.42, some small change. Okay, so you can see that it's running through the middle much better. So that's an example of slow response to fast excitation. It is an example of stabilization of a damped vertical inverted pendulum with base excitation at high frequency and small amplitude. The forces required are proportional to the amplitude and the square of the frequency. So the force required is order 1 over epsilon. A large force is required. There are lots of movies that you can find, YouTube videos and so on, which show the inverted pendulum becoming stable under base excitation. This general phenomenon of stabilization of an unstable equilibrium has many applications, including something called a Paul trap, on which I've done some work in the past. But here is for you an example of a calculation that was not terribly big. So first of all, if you look at the expressions, they were not very big. In principle, you can do them by hand. The second thing is that it's an application that shows slow response to fast excitation. It's a good application of the method of multiple scales, and it goes to second order before you can get something. The nonlinear terms are included, but even after including the nonlinear terms, what happens is that we get an equation where the forcing is not there. Because the forcing is not there, we are able to get a stability criterion, which otherwise you would have to determine from numerics through many simulations. Okay, that's it for this lecture. Thank you.